This is Chapter 8 on Process Management, Lean and Six Sigma in the Supply Chain. Here are your learning objectives. First, we're going to list and discuss the major elements of Lean and Six Sigma. Secondly, describing why Lean and Six Sigma are integral parts of supply chain management. Third, discuss the Toyota production system and its association with lean production. Fourth, discuss the linkage between lean programs and environmental protection. Fifth, describe the historical developments of Lean and Six Sigma. Sixth, describe and use the various tools of Six Sigma. And lastly, to understand the importance of statistical process control for improving quality. So, as a history introduction to Lean, in the 1990s, supply chain management combined quick response, efficient customer response, just-in-time and Keiretsu relationships to emerge as a philosophy and practices known as lean production or simply lean thinking. So lean production is basically an operating philosophy of waste reduction and value enhancement, and it was originally created as Toyota production system by key Toyota executives. So the early versions of Lean were based on Ford assembly plants and US supermarket distribution systems. The key concepts incorporated in TPS are MUDA, which talks about waste in all aspects of production, Kanban, which involves signal card and parts of JIT, statistical process control as part of TQM efforts, Pokayoki, error of mistake proofing, and Yokoten, which is on sharing of best practices. So lean production emphasizes on these issues: reduction of waste, continuous improvement, synchronization of material flows within the organization, and channel integration, which is extending partnerships in the supply chain. This slide explains about the relationship between lean thinking and supply chain management. So supply chain management seeks to incorporate lean elements using cross-training, satisfying internal customer demand, quickly moving products in the production system, communicating demand forecasts and production schedules up the supply chain, and optimizing inventory levels across the supply chain. So we have several elements of Lean, which includes waste elimination, lean supply chain relationships, lean layouts, inventory and setup time reduction, small batch production scheduling, continuous improvement, and workforce empowerment. So the next several slides would focus on the elements of Lean. So on waste reduction, firms reduce costs and add value by eliminating waste from the productive system. Waste encompasses wait times, inventories, material and people movement, processing steps, variability, and other non-value adding activities. So Taichi Ohno has described the 7 wastes, which includes overproducing, waiting, transportation, overprocessing, excess inventory, excess movement, and scrap and rework. Here are the 5 S, which includes, in English as term used, we have sort, set in order, sweep, standardize, and self-discipline. So for lean supply chain relationships, suppliers and customers work to remove waste, reduce costs, and improve quality and customer service. As in lean thinking, it includes delivering smaller quantities more frequently to point of use. So firms develop lean supply chain relationships with key customers, and they have mutual dependency and benefits which occurs among these partners. Locating production or warehousing facilities close to key customers is also under this lean supply chain relationships. For lean layouts, what we want to focus on is basically to move people and materials when and where they are needed as soon as possible. For lean layouts, they are very visual, so lines of visibility are unobstructed, with operators at one processing center able to monitor work at another. And we have this term manufacturing cells, which process similar parts or components, saving duplication of equipment and labor. They are often U-shaped to facilitate easier operator and material movements. So it's depicted here in figure 8.1, a U-shaped work cell. For inventory and setup time reduction, this is where excess inventory is regarded as a waste, and reducing inventory levels causes production problems. So once problems are detected, they can be solved. The end result is a smoother running organization with less inventory investment. We want to reduce purchase order quantities and production lot sizes. So this is a description that shows the relationship between order quantity, lot size, and average inventory. So when order quantity or lot size quantity is 100, your average inventory would be 50. But when your quantity that you order is reduced to 50, your average inventory falls to 25. So it involves this small batch production scheduling. So small batch scheduling drives down costs through reducing purchase, work in progress, and finished good inventories. It makes the firm more flexible to meet customer demand, and these small production batches are accomplished with the use of Kanbans. So Kanbans basically generate demand for parts at all stages of production, creating a pull system. So this is what small lot sizes looks like versus the large lot size approach. So with the small lot size approach, you notice that you are able to change 9 times or 9 different products in one production, versus a large lot size approach, which you could only change 3 times. So for continuous improvement, we have continuous approach to reduce process, delivery, and quality problems such as machine breakdown problems, setup problems, and internal quality problems. We have here a term called Kaizen Blitz, which is rapid improvement event or workshop to find big improvements quickly. The last one is on workforce commitment, where you have managers that support lean production by providing subordinates with the skills, tools, time, and other necessary resources to identify problems and implement solutions. This slide explains about the relationship between lean systems and the environment. So lean green practices will result in reduction of waste, reduction of cost of environmental management, leading to improved environmental performance, and also increasing the possibility that firms will adopt more advanced environmental management systems. So now we'll move on to understanding about Six Sigma. So Six Sigma is basically near quality perfection, where in statistical likelihood, it means non-defects of 99.99966% of the time, or 3.4 defects per million observations. It was pioneered by Motorola in 1987 and is a statistics-based decision-making framework designed to make significant quality improvements in value-adding processes. So this is a Six Sigma matrix, where at the last line here, you can see that if you achieve the 99.99966% defect-free output, you are also translating that you achieve the 3.4 units per million. Next, we're comparing Six Sigma and Lean. So here we have the term Lean Six Sigma or Lean Six. So this describes the combination of lean production and Six Sigma quality practices. So both practices use high quality input materials, work in process and finished goods, and also continuous improvement, or the term Kaizen. So Lean Six use complementary tool sets and are not competing philosophies. Now we move on to Six Sigma and supply chain management. So when we implement the Six Sigma in an organization, we are able to have this process integration and communication, which leads to fewer negative chain reactions along the supply chain. So the negative chain reactions could be in terms of greater levels of safety stock, lost time, or less productivity. Six Sigma is an enterprise and supply chain-wide philosophy that emphasizes a commitment towards excellence and encompasses suppliers, employees, and customers. Next, we move on to the elements of Six Sigma, which is attributed to Deming's 14 points. So as you can see here, Deming has identified 14 points to implement Six Sigma in an organization. Next, we have Crosby's contributions, which detailed out 4 absolutes of quality, which includes the definition of quality is conformance to requirements. Secondly, here he said that the system of quality is prevention. Third, the performance standard is zero defects. And lastly, the measure of quality is the price of non-conformance. Next, we look at Durand's contributions, which is the quality trilogy. The first one is on quality planning, where firms need to identify internal or external customers, their needs, then develop products that satisfy those needs, and managers need to set goals, priorities, and compare results. Secondly, on quality control, the firm needs to determine what to control, establish standards of performance, measure the performance, interpret the difference, and take action. Lastly, we have quality improvement. So the firm needs to show need for improvement, identify the projects for improvement, implement remedies, and finally provide control to maintain improvement. Next is on Malcolm Baldrige National Quality Award. So the 3 objectives of this quality award includes to stimulate firms to improve, recognize firms to quality achievements, and lastly establish guidelines so organizations can evaluate their improvement and provide guidance to others. So the 7 categories which are measured under this Malcolm Baldrige National Quality Award are these 7. Next, we move on to ISO 9000 and ISO 14000 families of management standards. So there are over 19,000 standards, and this specific standard 9000 and 14000 govern quality and environmental certification standards of production respectively. So ISO standards are voluntary, it's not a requirement for all organizations. So ISO requires review of its standards at least every 5 years, and it's a worldwide reputation as it is a generic management system standard. So the ISO 9000 standards were adopted in the US by ANSI and also ASQC. Next, we have the MAIC improvement cycle. So when firms decide to improve aspects in the production, they can go through this process, which first you define your problem, measure, analyze, improve, and then control. So further description of this whole cycle can be understood in this slide. Next, we have Six Sigma training levels. We have the yellow belt, green belt, black belt, and master black belt. So once you achieve the master black belt, you are basically a proven mastery of process variability reduction, waste reduction, and growth principles, and can be effectively present reigning at all levels. So we're done with the elements of Six Sigma. Now we move on to the statistical tools of Six Sigma. So there are 4 statistical tools of Six Sigma presented here. The first one is on flow diagrams, where it is an annotated boxes representing process to show the flow of products or customers. Secondly, we have check sheets, which determines frequencies for specific problems. Thirdly, Pareto charts presents data in an organized fashion, indicating process problems from most to least severe. And lastly, the cause and effect diagram, which is also known as the fishbone or Ishikawa diagram, which can be used to aid in brainstorming and isolating the causes of problem. So this is an example of a flow diagram or process map for a restaurant. Here we have an example of check sheet for problems at a restaurant. This is a Pareto chart for restaurant problems. So you can see here at the x-axis all the types of problems that are faced by this restaurant. Next is a Pareto chart to show the number of daily restaurant problems. And here we have the cause and effect diagram, which is on long wait problem. So on the left side, we have the 4 main issues, which are material, machinery, methods, and manpower. So under each issue, you have the related causes of problems. Next, we move on to the statistical process control. So this slide explains the purpose of a statistical process control. Number 1 here, it mentions that SPC allows firms to visually monitor process performance, compare the performance to desired levels or standards, and enables firms to take corrective action. So firms gather process performance data. They then create control charts to monitor process variability, and then collect sample measurements of the process over time and plot on the charts. So to create the process control chart, you basically need to understand these items. On natural variations, where when in a process for production, we would have natural variations. So it is something which is expected and random, and the firm cannot control. This is different to assignable variations, where there would be a specific cause and can be controlled by the firm. The next aspect that we need to understand is the difference between variable and attribute data. So for variable data, the measurement is continuous. So it can be in terms of weight, length, and time. Compared to attribute data means it's indicating some attribute such as color, satisfaction, or beauty. So the answer would be yes or no, good or bad. Now we move on to understanding more about statistical process control charts. So there are 2 types of chart, which is the variable control chart. So as I've mentioned in the previous slide, we have variable data and attribute data. So we'll start off the discussion on the process control chart with variable data. So there are 2 types of variable control chart, which is the X bar chart, that tracks central tendency of sample means, and the R chart, which tracks sample ranges. Sample range means you're taking into consideration in that sample the biggest measure minus the smallest measure. So the steps under this control chart: first, you have to gather data when the process is in control. Secondly, you calculate the mean and the range for each sample. Then you calculate the overall mean and average range of all the samples. We use the mean to calculate the upper and lower control limits. And then number 4, we use the means and control limits to construct the X bar chart and R control chart. And lastly, collect samples over time and plot so that we can monitor if there are any variabilities in our production. Here are the formula to identify our upper and lower control limits. This is an example of an X bar chart. This is an example of an R chart. So now we move on to the types of attribute data control charts. So it also has 2 types of charts. The first one is P chart, which monitors the percent defective in each sample. It's designated as P because we're identifying percent. Then we have the C chart, which identifies count on number of defects per unit of output. So C because we're identifying count. So this is a formula for the P chart. And the formula for upper and lower control limit for a P chart. This is an example of a figure for P chart. Then the C chart, this is your formula for your upper and lower control limits of a C chart. Okay, so the last aspect for the tools of Six Sigma, here we have acceptance sampling. So when shipments are received from suppliers, samples are taken and measured against the quality acceptance standard. So the shipment is assumed to have the same quality. Sampling is less time consuming than testing every unit that you get from your supplier, but it can result in errors. So there are 2 types of errors here. We have our producer's risk, where a buyer rejects a shipment of good quality units because the sample quality level did not meet the standard. This is called a type 1 error. And we have consumer's risk, where the buyer accepts a shipment of poor quality units because the sample falsely provides a positive answer. This is a type 2 error. So that's all for this chapter.